people that are absent. We'll see. Maybe someone will watch it, or maybe this is just sending my voice into the void forever, never to be heard. Am I right?
Congratulations, you're
Yes.
becoming a part of nothing.
I wonder if there's anyone, like, there's probably some way to find that information, like some person on Twitch who has been streaming every day for like years and has never had a single viewer. Do you think that exists? There's got to be someone, right? Sad. SAD, sad. All right, guys, we're gonna go over a few more examples today so that we can understand what we're doing. So looking at that, there's lots of things involved here. You see a function like this. You've got, for example, are there any x values that x can't be?
Yeah.
Yeah. So okay. So that is we use the word domain to talk about that. Domain x can be any number except for 2. Let's see. Are there any x values that make this whole function equal to 0?
Yes.
What? Which ones?
0.
0. Yeah. That we call that an x-intercept. If there's an x value that makes this whole thing equal to 0, basically, if there's something that makes the y value 0. Okay. Turns out that if you plug in 0, you'd have 0 divided by -2, which is 0. And then you go, wait a second, that's also the y-intercept, because the y-intercept is closely related, but it's, if you just plug in 0 for x and see what happens, well, in this case, it's the exact same point. So the only x-intercept is also the y-intercept for this function. And then what else? Vertical asymptotes.
2.
Yes, so it goes hand in hand with the domain. So x equals 2 is a vertical asymptote. And then to get the horizontal asymptote, you have to look at the end behavior. All right, this is I don't know. Would you guys agree that this is the hardest part?
Yes.
It's a resounding agreement. That's good. Okay, so what you got to do is think. There's sort of maybe there's 2 ways you can think about it. I would like it. Ideally, you should understand both. One is just numerically. Numerically speaking, who grows faster, an x squared or an x minus 2? They both grow. He grows faster. Okay, so he grows faster than him. And so if x was, say, like 1,000, you'd have 1,000,000 squared is 1,000,000. 1,000,000 divided by roughly 1,000. You go, okay, like if you take $1,000,000 and spread it out amongst 1,000 people, they each get about $1,000. That's pretty good. So what that shows you is that as x gets large, the whole function just gets large as well. So you can write this. And then how about as x goes negative? Well, similar idea, but this time you got to be really careful, because if x was negative 1,000, you'd have positive 1,000,000 divided by negative 1,000. So you'd actually be approaching negative infinity. Does that make sense?
Not really.
Not really, no?
Yes.
So then was that Taylor or Clarissa? You guys, is a jinx? So okay, so what part of that? So okay, say if I jotted it down as I was talking about it. I said, okay, here's x, here's y, and I said I picked 1,000 for my x value. Do you agree that 1,000 squared is 1,000,000? And would you agree that divided? I mean, would you agree that you're technically dividing by 998? That's pretty close to dividing by 1,000.
Yeah.
Pretty much the same. Would you agree that the y value is going to be roughly 1,000?
Yes.
Awesome, Anas. So do you see how that suggests that large x values produce large y values?
Yeah.
And then you got to go from that, and then you write that statement. So this says, if x is really big, then y is also really big. That's what that says. That's the sort of the thought process there. Now, there's another way. This is a very fast and efficient way. If you cover up the non-dominant terms, so if you say on top, there's only one term, so okay, that's the dominant term. On bottom, the dominant term is just the x, right? So cover up the 2, and what you can do is you can say, okay, my end behavior is going to be that y is approximately equal to, again, if x is big, x squared divided by x. Now, what's x squared divided by x? So do you see what I'm getting at here? Y equals x. We know that end behavior, don't we? So what this tells me is that if I just look at the ratio between the dominant terms, I can know the end behavior of the function. So a lot of students find this to be much easier than thinking about numbers. They say, I'm just going to basically use that technique of simplifying this down, right? Ignore the not dominant terms, so ignore the 2, simplify it, and you get y is roughly equal to x for large x values. Is this muddying the waters, or does this make sense, or glistening? Okay, thanks. That's good. So yeah, you can use this on any rational function. You can look for that and say, oh, okay, I know what y equals x looks like, so therefore I know the end behavior. So try that out if you're getting stuff. Okay. Now this is the really, I think, the most challenging part is, okay, I know how to list out all the information. How do I actually get that? How do I get a good sense of the graph?
What's the word on asymptote?
Oh, so horizontal asymptote. What do you think, guys? There isn't one. You only have, remember, this and this say the same thing. So if your y values aren't approaching a single number, then there's no horizontal asymptote. So let's just say, hypothetically, let's say as x approached infinity, y approached 7. Then what would I say here? Y equals 7, horizontal asymptote. If the y values aren't approaching some number, if they're just going to infinity, then we don't say there's a horizontal asymptote. Cool beans? Okay, so let's just go down piece by piece. Okay, let's see. Vertical asymptote at 2, sure. Follow the dashed line. There's my x equals 2. We got an x-intercept of 0, 0. That's also the y-intercept, so we only have 1 point to work with. And then we got the end behavior. So I know that far off on the right here, we've got approaching infinity. And then over here on the left, we have approaching infinity as well. Does that make sense with those arrows I just drew? By the way, some food for thought here. It actually is, this idea here goes beyond just the end behavior. It also tells you that this function gets more and more linear as x gets big. So this function would actually, in the long run, have the same slope as y equals x. It would actually have a slope of 1. And it's called hyperbolic behavior. So it's all curved. It's going to be curved in this region. And then in the long, if you looked way over here and zoomed in, you'd be like, that's a really flat, linear looking graph. So anyway, here, so some more interesting stuff. The guy that generated the x-intercept is x squared. So what do you think is going to happen at the 0? Bounce. It's going to bounce. Okay, so let's draw that in. So it's going to come up here. It's going to bounce off and go down to negative infinity. Is there a more concrete way to maybe test to make sure, like for example, the way I drew this, I'm saying that the y values are negative in between 0 and 2. What's an easy way to check that that's actually correct? Yeah, plug in any number between 0 and 2. I don't know, how about 1? Plug in 1, you get 1 over negative 1, which is negative. So that makes us feel pretty confident that that's correct. In fact, if you look at that, I hope it's somewhat, I wouldn't call it obvious, but like any number you pick that's between 0 and 2, is going to make the bottom negative. So anyway, can this guy cross the x-axis? We already listed out all the x-intercepts. We know there's no x-intercepts over here, so it can't cross. So it means it has to do something like this. Like that. Cool beans? This is pre-calculus. If you're thinking forward to the future math stuff you'll be learning in a calculus book course, you would then maybe be really interested in like, what is that point there? What's the lowest point on this part of the curve? And you'd be able to calculate that using the techniques of calculus. Next year, of course. I do want to show you something though. That's interesting. This is just enrichment, so you don't have to use these techniques, but I wanted to show this to you because it touches on this idea of this function is going to be approximately linear in the long term, which suggests that there's not a horizontal asymptote, but there might be some kind of diagonal asymptote. Has anyone ever heard of that, a diagonal asymptote? Maybe in Algebra 2? Hello, Cheyenne.
Hi.
What kind of PSL is that? What kind?
Oh, mine? Same me a paintbrush. It's like
Oh.
science.
Oh, science.
Yeah.
Nice. Okay, so anyway, I just want to really quick show you this. It's pretty interesting. So, and I'll show you something cool on Desmos. If you wait, I'm also curious. How many of you guys did like polynomial long division last year? Just maybe half yet.
Yeah.
Oh, you didn't work this way.
We did. I think. Oh, we did.
Here, something just to enrich your brains here. This goes into x squared x times that is x squared minus 2x. Subtract. I'm trying to bring it back to elementary school. Long division. 2x. Bring the 0 down. That goes into that 2 times. Multiply by 2. 2x minus 4. Subtract them. You get 4. There's your remainder. So it turns out that could have got written like x plus 2 plus a remainder of 4 over x minus 2. I don't really care if you remember polynomial long division. It's kind of an obscure topic, but this is interesting. This is something that you can think about. Look at this. What happens to this term if x is really big? Huh? It gets very small, right? So if x is large, then this term pretty much goes away, right? Which tells me that if x is big, the function is pretty much that. So what I can do then is I can actually show now, that's the diagonal asymptote. So I can show y equals x squared over x minus 2. And now I can visualize, here's the x plus 2, there's the diagonal asymptote. Let's make it orange. That's nice. And then let's put in the vertical asymptote as well. X equals 2, sorry. So that's kind of neato. And there you go. We can really see the function conform to those. Oh, sorry. Potential people watching this, if there's anyone out there. That's all I was showing is on Desmos. You can punch that into the computer. Now here's something else that's interesting, I think. What if it wasn't a 2? What if this is just like some number a? Oh, I messed up. What if this is just an a, some general constant? Let's set it to 2 temporarily. What if this is x plus a, this is x equals a, and then could you change the value of a? Look at that, that's pretty neato. Neato burrito. So you can see that like as that, watch what happens if you make x really small, or a really small, sorry. Look at that. What happened? You see what happened?
Very amused by this.
Well, if a was 0, you'd have y equals x squared over x, which is just y equals x. A flat line. Oh, come on. That's gold. That's epic gamer moment right there. Ooh. Pew. And as a gets bigger, it gets more, well, I can zoom out a bit. But you can see that this part just moves farther and farther away. Stretchy, stretchy.
Everything is moving and grooving.
Move, exactly. Moving and grooving. Moving and grooving. It's what worm? What's that? Is that from A Bug's Life or something? What is that? What is that? I don't know this. All right, let's do another one. I can see you're enthralled by that information there. Let's clarify something. Okay, I need to make sure this is clear as possible. Do you guys have to calculate diagonal asymptotes on this assignment? No. Yes. Oh, good. You guys are listening. So good.
So is that polynomial long division stuff? Could that be found in the ACT?
No. The most I can imagine an ACT question asking you in regards to like rational functions and stuff is, they might ask you. I'm trying to think of an example I've seen once. They might give you a function like this and just ask you like, for what x values is this function undefined? They might ask you that, in which case you'd put in the numbers that make the bottom 0. I've seen some where they require you to like cancel out a common term from top and bottom of a fraction. But yeah, I've never, in all my years, I've never seen a question asking you to do polynomial long division. What? Interesting. But no, that won't be. Trust me, it's not going to be on there. The ACT will put some weird questions on there. In the last few years, I've seen them randomly put on questions about matrix multiplication, which is like so out of left field. I don't know why they put that on there. But anyway, if you're taking the ACT, I would just recommend take some practice tests, see what kind of questions are on there. You'll notice that 80 to 90% of the questions on there follow a very simple pattern. Like they just come up over and over and over again. And you can kind of train yourself to just recognize the types of questions that they're going to put on. And then they kind of pepper in a few random weird ones from time to time. Pepper. That's a verb, right?
Yeah.
Whoa.
Thanks, Sarita.
Instead of an F, what's going on?
What?
It's TX, not FX.
Uh-oh. It's a different letter. 22 has H in it, son. Watch out for that one. I can't process this. This is like back in like middle school when you've been doing like this. X plus 2 equals 6 for a while. And I think I got it. And the teacher throws this at you. What if it's A plus 3 equals 10? You're like, Dad, you can't solve that. That's not possible. I only can do it if there's an X. No, they're just symbols. Or you do a word problem that turns out that it's the solution is, the guy bought 20 watermelons. Oh my goodness, that's so dumb. No one ever buy 20 watermelons. Oh.
Maybe he needed his snack. Maybe he was doing a rubber band.
Okay. The next question. Hopefully when you see that top there, you think, I should factor that. It'll give me extra information. So we factor it. Let's see. Factoring that gets us, we need two numbers that multiply to be -2. The average -1, so it's -2 and a +1. Cool beans, right? Easy peasy? All right, let's get the domain. There's only one number that x is not allowed to be. 1. This can't be 1. And that is going to be a vertical asymptote. Remember, guys, these go hand in hand. They're not really the same thing, but they're just very closely related, closely connected. Okay. Let's get some x-intercepts on there. 2. Remember, x-intercepts are points. They have an x and a y coordinate. I know it might seem silly, but you're like, well, the y coordinate's always 0. Yes, it is. So 2, 0, and negative 1, 0 are the two x-intercepts. Let's get a y-intercept next. I'm not going too fast, right?
No.
Y-intercept. The trick there is you just plug in 0 for x and see what happens. So let's look up there. Very good. The answer's 2. So you go. Some people in the last class were plugging it in here. Is that wrong? No, not wrong, but it's a lot of times easier to plug it into the original, because just imagine all these x's turning into zeros. And now you got negative 2 divided by negative 1, which is 2. If you plug it in here, you got to keep track of it a little bit more in your head. You got to go negative 2 times 1 divided by negative 1. So just slightly more to keep track of, I guess. And behavior. Okay, dramatic pause. Hopefully this one is, hopefully we know this one. Because there's a similar function right above it that we just talked about. You might go, yeah, but they're different functions. Yeah, they are different functions, but if you boil this down to only its dominant terms, dominant term on top is x squared, dominant term on bottom is x. See how it's the same, right? Yeah. So my end behavior is basically going to be like, it's going to be y is roughly equal to x for large x values. So,
Why is it y?
because if x is big,
Oh.
then you basically have, so if x is big, then y is roughly equal to x squared over x. So I ignored the non-dominant terms, which would basically give me y equals x. So now,
It's right.
this is like the mathematical way to write the end behavior. But this, I think this is a very strong statement, strong mathematical statement, because it tells you a lot about how the function behaves. Y equals x looks like this, so we know the end behavior is positive infinity on the right, negative infinity on the left. All right, so beep. I've got to listen to those beeps all day. It's pretty good. Vertical asymptote at 1. Put that guy in there. There's the vertical asymptote. X-intercepts at 2 and negative 1. Let's put those on there. Y-intercept at 0, 2. Let's put that on there. And that's all the info we can put on the graph so far, right? Did I miss anything?
There's no horizontal.
Ooh, yeah. You're right, though. We should say that there is no. There is no horizontal asymptote. Although I don't know why he's angry. It's not like, I don't know. Not existing is not necessarily bad. But it's not necessarily good either. Let's make it neutral. There you go. Just doesn't exist. The state of non-existence. He just is. Or he isn't, sorry. He doesn't exist. Okay, who knows what this looks like? You see it? It's got to do... Oh, by the way, again, look who created that intercept. This term He's not squared, right? So he's going to pass through at 2. He's also going to pass through at -1. Does that make sense?
Yeah.
Not going to be bouncy. So no bouncies. And again, there would be some kind of diagonal asymptote if you're curious, but we're not going to concern ourselves with finding it. In this case, I think it's y equals x, if you're wondering. Actually turns out just to be y equals x. Okay, I want you guys to try some on your own here. We'll go over at least one of the solutions. But 21 and 22. What do you notice about 21 and 22? True, that's true of 21. Think more broadly about this. Look at them together.
They're reciprocal.
What's that word? Reciprocals. They are reciprocal functions. So my intent here with this pair of questions is for you to, well, one, graph them, think about where's the asymptotes, where's the intercepts, but then think, once you get them both done, try to think more deeply about the connections between the two graphs, because they are reciprocals of each other. So you're going to see some connections between, say, like intercepts and asymptotes. So anyway, food for thought. Go ahead and try them out. Take maybe 10 minutes roughly, and then we'll go over at least one of the answers. I'll just leave this.
Yes.
Actually, I think I'll just end the stream here, because if anyone is watching this, you can just, we've gone over the techniques. You'll be fine. Send Travis Scott burgers. Don't forget, go to A&W, 7:59 p.m. Order 30 Travis Scott burgers.
I think we missed